Okay, so please give me a quick nod if you can hear me. Great. So I was asked to give a modern infinity categorical exposition of the topological six-functor formalism, which is great, except for the fact that no such modern treatment exists, at least not in full generality. So I decided to tell you what I think should exist, and therefore the title is just a roadmap to topological six-functor formalism. In particular, I'm not sure that I got all of the technical details needed for all of this machinery to work. As I said, not all of it has been constructed. Okay, so the topological six functors formalism is about six operations you can perform on sheaves, or more explicitly on complexes on sheaves, and how these interact with one another formally, and what you can formally deduce from these relations. But before giving you the list of my six functors, or of Grothendieck's six functors, let me first tell you what he's trying to generalize. And what he's trying to generalize is the idea of Borel-Moore homology and compactly supported homology, and it's going to be generalized into families. But before we have it in families, let's look at a specific classical example, just that we have something in mind when we discuss these six functors. So classically, the story starts with Poincaré duality. If you have a topological space X, which is actually a manifold of dimension n, and it's compact and orientable, then the cohomology of X is the same as the homology of X. Well, and they're not the same. They are interchanged up to a shift and a minus here. And this is a classical Poincaré duality that we all know and love. However, if X is non-compact, then this statement doesn't hold as written, at least if you interpret homology and cohomology to mean singular homology and cohomology. Now, what you can do is to try to fix this by tweaking the definitions. And you actually have two choices here. You can either change the definition of cohomology to cohomology with compact support, or you can change the definition of homology to Borel-Moore homology. So I'm going to quickly review what are these things, just so we have some concrete object in mind. And to be consistent with the rest of this talk, and for simplicity, I'm always going to assume that my coefficients are over a field K. So, first of all, let's define cohomology with compact support. So, here is a definition. If you have a topological space X, you can go over all of its compact subsets and look at the relative cohomology of X relative to the complement of your compact subset. And unwinding these definitions, you can see that this is the same as taking the homology of a subcomplex of cochains on X, which is called the subcomplex of compactly supported chains. And these are exactly the cochains that vanish outside of some compact K. And of course, since we have an inclusion of complexes, when we take cohomology, we get a natural transformation. So we always have a natural transformation from compactly supported cohomology to the cohomology of X. And as an example, we can calculate the compactly supported cohomology of Rn. This could be done, well, the definition tells you that you have to consider all compact subsets of Rn, but if you just look at the closed balls of radius r. This is a cofinal system in them, so we can just take the colimit on these compact disks, and the relative cohomology of Rn relative to the complement of this closed disk is k in degree n and 0 otherwise. In particular, it's not the same as the regular cohomology of Rn. So we do see that this is an invariant that is not a homotopy invariant, but it does depend on the actual topology of the space. However, in many reasonable cases, we can reform this path from homology to homotopy using one-point compactification. So let's denote by x plus the one-point compactification of x. And if this one-point compactification is reasonable, if the point in infinity has a locally contractible neighborhood, then the compactly supported cohomology of x actually agrees with the cohomology of the one-point compactification relative to that point of infinity, or in other words, the reduced cohomology of the one-point compactification as a point in space. And finally, I wanted to mention that unlike regular cohomology, which is contravariant, the cohomology with compact support actually extends to a covariant functor. If I have a map from x to y, I get a map in the same direction between the compactly supported cohomologies. Okay, so that was our compactly supported cohomology.
Question?
Yes.
It's covariantly functorial with respect to which kind of maps? All maps?
All continuous maps, as far as I remember.
Okay.
Okay. So that was one side of our generalized Poincaré duality, but we also have another possibility, and that's to use Borel-Moore cohomology. That is the homology of the complex of locally finite chains. So usually a chain is just a formal sum of singular simplexes, but these locally finite chains are actually an infinite formal sum. And we're only taking the infinite formal sums that sort of satisfy the following finiteness condition. For every compact K, compact subset K, if you look at the chains that actually, at the simplexes, the singular simplexes that actually appear in the sum, and so only a finite number of them are going to intersect K. So if you just take these to be your locally finite singular chains, arrange them in a complex, and you get a definition of the Borel-Moore homology. And again, if X is reasonable, then the Borel-Moore homology is actually the reduced homology of the one-point compactification. And as an example, the Borel-Moore homology of Rn is the Borel-Moore homology of its one-point compactification, which is n, k in degree n, and 0 otherwise. And just for completeness, let me say that this can be extended to a contravariant map. So if I have a map f from x to y, I get a map in the other direction from the Borel-Moore homology of y to the Borel-Moore homology of x.
You need the map to be proper for that.
I need the map to be proper?
Yeah.
That's maybe. I mean, possibly. With this definition, possibly. I'm not sure.
No, yes, I'm quite positive. Yes, you need that.
Okay, so you know, let's put it with respect to proper maps. Sure. Okay. Now, with this prelude, we're going to go on directly to list 6 operations that we can perform on complexes of sheaves. So for that, I'm going to need.
Let me I'll just say that. So one thing that you can see, okay, is that you know, you can map. You can write R as a retract of R squared, right? Right? R goes to R squared goes to R. So if this thing was contravariant, you would get that you would get that a one-dimensional vector space is a retract of a zero-dimensional vector space. If you look at it,
you're right.
Right? So it has to be proper, otherwise it's the same with the other thing, with the cohomology supported cohomology. It has to be proper now.
Yeah.
I'm sorry, but I'm actually a bit confused about this point. So it seems to me that cohomology with compact support is naturally contravariantly functorial with respect to proper maps.
Yes, you guys are
kind of
very correct.
No, sorry, I was saying something else, that
it's contravariant.
Contravariantly functorial with respect to proper maps.
Contravariant, no, that's.
But I think that there are situations in which it is also covariantly functorial, but with respect to some kind of like open embeddings or something. No?
Yes, that's true. There's a
So the kind of functoriality we're talking here is just like with ordinary homology and cohomology, like the co and contra, but only for proper maps. So this is the statement, right?
yes.
Okay.
Okay.
The Borel-Moore homology is covariantly functorial for proper maps.
I would like to continue instead of discussing the functoriality, because this is just a prelude.
Yes, let's ignore this.
A lot to cover. Okay. I'm not, so this ends our prelude about Poincaré duality. There is an issue here about the functoriality of these classical constructions, which I'm not going to address now, because I'm not sure what exact details I need. They might only be functorial with respect to some maps, but this is only a prelude to the 6 functors that we want to discuss. So for that, to discuss these 6 functors, I'm going to have to tell you what they operate on. So, and they are going to operate on sheaves, or more specifically, complexes on sheaves. So let me tell you what are the conventions that we're going to have here. Oh, yeah, I did want to mention that we got Poincaré, extended Poincaré duality, but it still only works for orientable manifolds. For non-orientable manifolds, we will have to introduce the former twist, either using either a local system or by expressing everything in sheaf cohomology and twisting by the orientation sheaf of our manifold. And that's also a phenomena that we will encounter in the next part. Okay, so I will need some conventions to talk about sheaves. So first of all, my sheaves are all going to be on locally compact Hausdorff topological spaces. And I do mean topological spaces. I am generalizing constructions that depend on the topological space and not on its homotopy type. And the values of my sheaves are going to live in the category of chain complexes of K vector space. So, or in the derived category of chain complexes of K vector spaces, which for some of the people here, vect K, this derived category, might be more familiar in its description as HK module in spectrum. In particular, it's a presentable category. And I'm going to use, just like Tomer did, I'm going to use a cohomological indexing for my chain complexes. And I want to note two more things. First of all, that vec K has a tensor product. So it's a closed symmetric monoidal structure. It has an internal Hohmann tensor product, which I'm going to use. And second, I'm going to denote by cut K all of the stable, presentable K linear categories, which, if you want a precise definition, this is just modules over vect K in PRL. And I just wanted to note that in particular, when I talk about a morphism in cut K or a K linear functor, I'm assuming that it preserves colimits. Okay, so now we have.
What is PRL? Like, even what does it stand for?
This is the infinity category of presentable infinity categories and
Cool.
limit preserving functors.
Mm-hmm.
Okay, but it's a classical theory of Schwede and Shipley from the 90s that this infinity category vect K is equivalent to chain complexes of K vector spaces. Okay, so with these conventions, let's talk about the 6 functors. And these are going to be a tensor product and an internal Hom on sheaves, the pullback and push forward functors, the push forward with exceptional support and pullback with, push forward with compact support and exceptional pullback. So my categories, my category of sheaves is just going to be the full subcategory of contravariant functors from the set of open subsets in X to vect K. And the tensor product on vect K followed by sheafification endows this category with a closed symmetric monoidal structure. So in particular, for every sheaf on F on X, I get two adjoint functors tensoring with F and homing from F. That takes care of these 2 functors. And let me also mention that there is an alternative description if you know that sheaves on a product X times Y is equivalent to sheaves on X tensor sheaves on Y over sheaves on K, where this here is Lurie's tensor product on PRL, on presentable infinity categories. So using that fact and pulling along the diagonal, which is what we're going to discuss next, you can define the product, the tensor product, as a map from sheaves X times X to sheaves X tensor sheaves X over vect V, and then pull back along the diagonal back to sheaves X, which gives you a way to tensor two sheaves. Okay, so next let's discuss pullback and push forward, which are also called the direct and inverse image. So for every continuous map, we have the following induced maps. The inverse image map F upper star from sheaves of Y back to sheaves of X, and the direct image from sheaves of X to sheaves of Y. The direct image has a very classical description. If you give me a sheaf F over X and you push it forward to Y, then its action on an open subset of Y is just given by pulling that subset, looking at the pre-image of the subset in X and taking the sheaf over that. The push forward has a slightly more involved definition, but you can still describe it as a sheafification of a pre-sheaf on Y. It's a pre-sheaf that sends every open subset to the colimit on FV, where FV are all the opens in X that include the inverse image of F. And alternatively, or in a more modern perspective, you can define this left adjoint by starting with the function of posets that sends an open subset in Y to its pre-image in X, taking pre-sheaves, tensoring with vect K, and then further restricting to sheaves. Okay, so just some examples, so this would not be too outlandish. If I have a point, or a map from a point to X, and a sheaf on X, then I can pull this, then X upper star of F is just a stock F of F at X. And if I have a in vect K, then X lower star A is just a skyscraper sheaf concentrated in X. And similarly, if I have an open subset, then the inverse image along the inclusion is just a restriction of the functor, and the direct image is extension by zero. Okay. Yes.
Usually what people call extension by zero is not the push forward.
Yeah, you want to, I'll call it extension. I think that for open, this also includes extension by zero, but
no, the lower star is not the extension by zero.
For close, it will be extension by zero, but for
close, it will be.
The point is that if you have a point on the boundary of U, you want to ask what is the stock at this point. So for the lower star, it will have a non-trivial stock usually, and extension by zero is the other thing for which the stock would be zero outside of it. Yes,
you're right. This is the extension not by zero.
Yeah, it's extension, but not by zero.
Not by zero, but yeah, for an inclusion of a closed
extension by fiat.
This is an extension by zero. Okay, so using this direct and inverse images already allows us to define a notion of cohomology using sheaves. And this goes as forward. We're going to use the map from X to a point, which I'll just denote P, which induces our adjoint pair, P upper shriek, P lower shriek, and give the following definitions. If I have a sheaf X, a sheaf F on X, then the global sections of F are just going to be the push forward of F to a vector space. And notice that since I'm over a field, in order to describe an object in vect K, I can just describe its cohomologies as a graded vector space. So this is really just a sophisticated way of saying the sheaf cohomology. And the constant sheaf is going to be what I back an A in vect along this map P lower P upper streak, lower streak. Do I have it wrong here? P.
I think you're good.
Say again. What's the problem? What's the question? Sorry.
I'm worried about this adjunction.
Well,
Looks
it's
great.
the other.
No?
No, it's you
Yeah.
pull from it. No, the other. The other way around.
This, yeah,
Right,
this
that's
just
the
looks
way
wrong.
Yeah.
Just the upper.
P, but this goes from vect, which is sheaves along the point, back to sheaves on X and P lower streak.
What's important here is that P upper star is a left adjoint.
This is completely true. Okay, so with global sections and the constant sheaf, we're going to define the sheaf cohomology just as the cohomology of this chain complex of global sections. And the usual cohomology of X with values in A is just going to be the cohomology of X with values in this local, in this constant sheaf of A, or really just the cohomology of A pulled back, pushed forward. And if I'm just saying the cohomology of A, then this means that I'm just taking the vector space K concentrated in degree 0, which is a unit there, and taking cohomology with respect to that. So just cohomology of pull back and push forward of the unit of vector K. And we have the following nice result. If X is locally contractible, then this is the same, this is isomorphic to the singular homology. Okay. Next. Next, we want to discuss the direct image with compact support and the exceptional inverse image, which are these pair of functors that we have for every continuous map from X to Y. So the classical way of describing this is to say that F lower shriek is actually the derived functor of a classical functor to the vector, to the heart of vector spaces. So to chain complexes concentrated in degree 0, which sends U to sections of the push forward for which they include the map from the support of the section to U is a proper map. Now, of course, for us, a better and alternative description would use the following fact. If you have a compact subset in a space X, then you can define f of k to be the colimit of all of the f of u's that contain k. And in fact, this information can capture all of the behavior of the sheaf F as long as your space is reasonable, is locally compact. So for locally compact subsets, for locally compact Hausdorff topological spaces, we actually have an equivalence between sheaves on X, which are described by functor from the from open subsets, to sheaves which are described as functors from the compact subsets of X. And since compact subsets have always an image which is compact in this locally compact Hausdorff situation, this induces a map from the poset of compact subsets in X to the compact subsets in Y, and again we can pass to the pre-sheaves tensor with vect K and localize to sheaves. So this gives us a definition of F lower shriek, which has a right adjoint called F upper shriek, or exceptional inverse image, with this alternative description is just given by definition, because we've constructed a colimit preserving functor between presentable infinity categories. However, I should note that this left adjoint is a derived functor of a classical functor, while this F upper adjoint, this F upper shriek, is not a derived functor of anything. There is no classical construction behind it. Okay.
I just want a small remark. In the future, in algebraic geometry, F lower shriek will also not be like, at least not the naive derived functor of the ordinary push forward with compact support. So in algebraic geometry, both things will be not derived functors in the obvious way.
Okay, right. So finally, and maybe this is more apparent from the classical description in which we just defined F lower shriek F of U as a subset of F lower star F of U, is that we have a natural transformation from F lower shriek to F lower star. And you should really think about this as a generalization of the inclusion of cohomology with compact support in the regular cohomology. And to do that, I want to tell you how to define cohomology with compact support using this adjoint pair. So again, we're going to use the same map, which now gives us a P lower shriek from sheaves of X to vector K, and P upper shriek from vector K back to sheaves of X. The global sections with compact support are just going to be defined as P lower shriek of F. And this allows us to define cohomology with compact support as the homology of this chain complex of compactly supported chains. And of course, the cohomology of compact support with X will just be the cohomology of compact support in the constant sheaf K, which is just the P lower shriek, P upper star of the unit. Now, in fact, we can actually use this to define a version of homology. And this goes as follows. First, let us define the dualizing sheaf, which is a sheaf of X, or really a complex of sheaves of X on X, as P upper shriek of K, or P upper shriek of the unit. And using this dualizing sheaf, the homology of X will be defined as the cohomology with compact support of X with coefficients in the dualizing sheaf, or just the cohomology of the homology of P lower shriek, P upper shriek of the unit. And finally, the Borel-Moore homology is going to be defined as, the same thing, but when taking cohomology with no compact support, so just the homology of P lower star, P upper shriek of the unit. And in order to relate this strange and new dualizing sheaf to something that we know, we have the following fact. If X is a manifold of dimension n, then this dualizing sheaf is in fact concentrated in degree n. And in this degree, it's just the orientation sheaf of our manifold n.
Asaf, I think in the chat, it appears to be some confusion about whether the lower shriek is the left or the right adjoint of the upper.
The lower shriek is the left adjoint.
Okay, thank you very much.
The lower shriek and the upper star will be the left adjoints for us. Okay, so if X is also oriented, then it of course follows that the dualizing sheaf is just constant, concentrated in degree n, from which we can immediately get Poincaré duality. So taking cohomology with compact support of that statement, we immediately get that the cohomology with compact support of X is isomorphic to the homology of compact support with X when we changed our indexes as follows. Just because all of these functors are exact, so they interchange with shifting by n. So taking cohomology support of k, of X with values in k, is the same as P lower shriek of k, but that's the same as P lower shriek of the dualizing sheaf shifted by n and minus n, which is the same as the cohomology with compact support with values in the dualizing sheaf shifted by n, whose homology, and our definition of homology was just the cohomology of this sheaf. And similarly, taking global sections retrieves the other generalization of Poincaré duality between homology, cohomology, and Borel-Moore homology.
Asaf, a small remark. If you're like me, then you cannot possibly ever understand the shift conventions. So a thing to say, which is coordinate invariant, is that the dualizing sheaf is the suspension n of the constant sheaf for the oriented manifold. Suspension n doesn't depend on conventions because it is defined by categorical properties.
Okay, if this helps you, why not? Okay, so now we have our characters, the 6 operations that we can perform on sheaves, and our next goal is to list some properties that tell us how these are related or how these interact with each other. And we're going to have 2 types of interactions. The first is going to fall generally under base change and tell us how the 2 push-pull joints are related. And the other is going to tell us what is the relation with symmetric monoidal structure. And in general, what we'll have there is a projection formula. So let's start with the first. The interaction between F lower shriek, F upper star, F lower star, and F lower shriek, F upper shriek. And what we have is these 2 properties. First of all, whenever I have a map F from X to Y, I have a natural transformation from F lower shriek F to F lower star F. And we already talked about this natural transformation. And the property is that if my map F is actually proper, then then this map is an equivalence. So F lower star, F lower shriek is equivalent to F lower star. And the second main property is base change. So suppose that you have 2 topological spaces over S, which is we think about as 2 S families of topological spaces, and we're taking their fibered product. Then given a sheaf F over Y, I can either push it forward to S and then pull it forward to a sheaf on X, or pull it along the projection and then push it forward to X. Base change tells us that these operations agree as long as I'm pushing forward using the lower shrieks and pulling back using upper stars. So taking push forward with compact support and regular inverse image. And putting these two together tells me that if the map G here is proper, then I can change the lower shrieks here to lower stars. And of course, just by passing two adjoints, we get an implication, an equivalence between their adjoints. Okay, so we have our interaction between these two functors. What about the symmetric monoidal structure? So here are the two things that you need to know about how these functors interact with the symmetric monoidal structure. First of all, F upper star, the usual inverse image, is a symmetric monoidal functor. And from this, formally, just by applying Juneda, we get the following conclusion. If F is a sheaf on X and E is a dualizable sheaf on Y, then pushing F and tensoring with E is the same as first pulling E, then tensoring with F over X, and then pushing forward again to Y, which sometimes is called a projection formula. However, what is more usually called the projection formula is the interaction between F lower shriek, the push forward with compact support, and the symmetric monoidal structure, which gives us a very similar which tells us that a very similar formula holds for F lower shriek now, and now it holds for every sheaves F and E as above. And there is a categorical way to repackage this projection formula. And as a slogan, the projection formula is saying that F lower shriek is a morphism of sheaves Y modules. So what does it mean, sheaves Y modules? So recall from the top of the page that F upper shriek is a symmetric monoidal functor, which just means that it's a morphism of commutative algebras in cut K. And every morphism of commutative algebras makes the target a module over the source. Or more explicitly here, sheaves of X on X will be a sheaves Y module in the sense that it will have a multiplication structure given by our ability to tensor a sheaf on X with a sheaf on Y and get a sheaf on X back. And we just do it by pulling our sheaf on Y back to a sheaf on X using F, and then tensoring on F. And if you unwind what this formula means, this just means that our action on a sheaf on Y and then applying our morphism of sheaf on Y is the same as applying our morphism of sheaf on Y and then acting by our scalar. Okay, so we have 6 functors. We have stated some of their properties. And the next thing that I want to tell you is that this has a lot of formal implications. So I don't want you to understand all of these formal implications. I just want you to get an impression of what sort of formal implications do we get from free, just from knowing these facts. So first of all, using the fact that our symmetric monoidal structure is closed, the projection formula induces these formulas on internal homes. So if you're trying to calculate an internal home from F lower shriek to E, it's the same as taking the internal home to F upper star and then pushing forward. And similarly, pulling back an internal home using the exceptional inverse image is the same as the internal home from F lower shriek to F upper star. And from this, if F is dualizable, then F upper star of a tensor product is the same as, sorry, F upper shriek of a tensor product is the same as F upper star of the first element tensor with the F upper shriek of the second. This is sometimes known as local Verdier duality. So some more implications. Using our dualizing sheaf omega x, we can define a functor called the Verdier dual from sheaves to sheaves, a contravariant functor actually, which is just the internal home into the dualizing complex. And taking these formulas together with this definition, we get a very close relation between the shriek notation, the star notation, and Verdier duality. In fact, Verdier duality interchanges F lower shriek and F upper shriek. Some of this is just an immediate consequence, and some of it depends on the fact that the dualizing sheaf is in the Picard group. So it's tensoring it with Fx dual is equivalent to the unit. This ensures that this Verdier duality functor is an involution on dualizable objects, so on perfect complexes.
Question. So theoretically, just like to make sure I understand things, what the operation of lower shriek and upper shriek was defined in a kind of a complicated way using this restricting to compact spaces and then doing something. Mm-hmm. Theoretically, one could define this Verdier duality also in similarly complicated way with restricting to compact subspaces and so on, but just to define it and then using it and the stars to define the shrieks, right? Like it's formally equivalent pieces of data.
Yes, as far as I know, there are many ways of stating what the six-functor formalism is. You have to describe all of the relations, and you do it by choosing a specific set of properties and focusing on these properties. So I chose a specific set of properties with some goal in mind. But an alternative description would be to describe the F lower shriek and F upper shriek using Verdier duality. And I just want to say that a formal implication of Verdier duality under the condition that the dualizing sheaf is in the Picard group is the duality between the homology and cohomology. Just formally follows. We also get the following version of Kuhn's theorem. If again we have our fibered product and we denote this map to S using delta, then we can, given E a sheaf on X, sorry, F a sheaf on X and E a sheaf on Y, we can pull them back using the projections to get sheaves on the fibered product and then just tensor them there. And our sheaf version of Kuhn's theorem says that the direct image with compact support along this delta, which I just think about as taking fiber-wise cohomology with compact support of this tensor product, this box tensor product, is the same as just taking F lower shriek and G lower shriek of our two sheaves and tensoring them in S. And the proof, I'm not going to go over it, I just want to show you how short it is given our formalism. It's just an application of the projection formula for this functor here. followed by base change for the pullback shift that we got here. And then we plug that in to our, and calculate delta lower shriek of the box product, and using the projection formula again, get the result. Okay, so we have our 6 operations. We have a list of properties between them, and these have a lot of formal implications. So the last thing that I want to do, or maybe next to last thing, is tell you how one can imagine packing these things using higher categorical formalism. And this is the dream part. No one has actually constructed such a functor, but let me tell you what I imagine could be true following ideas of Gates, Corey, and Rosenblum. So what we have the following 7 things. For every x, we associate sheaves of x, a k-linear category. For every map f, we associate 2 k-linear functors, f upper star and f lower shriek. These are related by the base change formula. Each sheaves of x is a closed symmetric monoidal structure. F upper shriek is symmetric monoidal. We have the projection formula, i.e. F lower shriek is a morphisms of sheaf y modules. And there's a natural transformation from F upper shriek, F lower shriek to the identity. And if F is proper, then this natural transformation is a counit of an adjunction between F upper star and F lower shriek. So this is just a restatement of the natural transformation from F lower shriek to F lower star. And the fact that this is an equivalence if F is proper, I just restated it for the left adjuncts. And here is the slogan of how we're going, of what packs all of these properties together. These facts 1 to 7 are the same as saying that we have a functor from some category to k-linear categories, which is a symmetric monoidal infinity 2 functor. So that's a lot to say, and let me just try to indicate how does such a categorical construction pack all of these properties. So first of all, I have to tell you what is this category of on the left-hand side. So let's start just with the 1 category. I'm looking at...
You have roughly 20 minutes, just so that you keep on time. And you wanted to talk about the trace also, I know. So
I know.
Yeah, okay. Just so
I know. Okay, so I want to describe how these two are related. So first, let me tell you what is the 1 category before extending it to a 2 category. Our 1 category is a category of correspondences or spans of locally compact Hausdorff spaces. So the objects are just our old spaces, and the morphism is just a span from X to Y. The composition of 2 morphisms is just given by taking a pullback. And note that every correspondence could be decomposed to a correspondence that has only something on the backward going leg and only something, and then only something, a correspondence that is right going. So if I'm trying to describe a functor from correspondences to cut infinity, then this is what my proposed functor is going to do. It's going to take every space to sheaves on X. It's going to take every forward going leg to the left adjoint F lower shriek. It's going to take every backward forming leg to the left adjoint F upper star. Using this decomposition, this tells me where it sends all of the morphisms. And the fact that this is a functor, or it it respects composition, will tell me that these pullback squares here have to go to commuting squares, which will just give me the base change. Okay, so that's just a one functor, but we also said that it's symmetric monoidal. So just to be on the same page, the symmetric monoidal structure on this category of correspondences is given by taking product of spaces. And if I have two spans, I'm just taking the product of each of the spaces of the span pointwise. And note that this already has a lot of structure. For example, every object in correspondences is a commutative algebra. In fact, its multiplication is given by this span, given where here I have just a diagonal map. Now, since sheaves is a symmetric monoidal functor, this immediately tells me that sheaves X is a commutative algebra in cut K, or a closed symmetric monoidal infinity category, with tensor product given by the equivalence from sheaves X times tensor sheaves X to sheaves X times X, and then pulling back along this functor. Second of all, if I have a backward going correspondence, then you can actually check, it's a nice exercise in unwinding the definitions, that this is a morphism of commutative algebras in this category of correspondences. And since sheaves is symmetric monoidal, this will tell me that that F upper star is a symmetric monoidal functor. Similarly, each forward-going leg is a morphism of Y modules. So applying a symmetric monoidal functor will tell me that F lower shriek is a morphism of sheaves Y modules. So we got the projection formula. So we just have to deal with this natural transformation from F lower shriek to F lower star, which is an equivalence if F is proper. And we're going to do that using the infinity 2 categorical part. So first, I just wanted to say that I'm thinking of cut K as an infinity 2 category, where the two morphisms are just natural morphisms and transformations. There's nothing special here. But I'm going to define the two morphisms on correspondences as follows. If I have two correspondences, Z0 and Z1 from X to Y, then a two morphism is given by such a commutative diagram where the map F is proper. And I'm going to denote that by correspondences in locally compact house of spaces, subscript proper. And our functor was actually a functor from this category when I invert all of my two morphisms. So if I have a proper morphism F from Z0 to Z1, I'm going to get a natural transformation in the other direction between the associated functors. And now just from this, you can look at the following correspondence. Here I am taking F and F and get the fiber product of X times X over Y. And this receives a map from F, which is proper, from X, which is proper. So it induces a natural transformation in the other direction, which is exactly the candidate to the unit that we wanted. Moreover, if F is proper, we also have this correspondence, and applying sheaves gives us a unit for the previous adjunction. So we deduce that F lower shriek and F upper star, or two left adjoints, are actually adjoint to each other if F is proper. In other words, for F proper, F lower star and F upper shriek agree. Okay.
Asaf, where did you use properness?
Sorry?
did you use the geometric property or properness for this adjunction?
I use.
Well, I mean, well, I'm confused about this, but maybe we should move on because we don't have a lot of time.
So what's missing is to use geometric properties of properness to construct a symmetric monoidal infinity to functor. But we can discuss this.
I see. It's not in this description. It's in the fact that you can construct it.
Yes, this is a formalism.
Okay.
If one will construct such a symmetric monoidal infinity to functor for you, then you will get all of the properties of these 6 functors and all of the formal consequences. Okay, so finally, I was asked to talk about categorical traces and Lefschetz fixed points. So let me just remind you that if we're in a closed symmetric monoidal infinity category E, and we have an endomorphism of a dualizable object, then we can always define the trace of F, which is an endomorphism from the unit to the unit, using the evaluation map, F times the identity on the dual, and then the co-evaluation map. And the dimension or Euler character of an object is just a trace of its identity. So, for example, in vector K, the dualizable objects are exactly those which have bounded finite dimensional cohomologies. The trace of such F is exactly this, the trace of the map induced on cohomologies with this alternating sum. And the Euler character is the Euler character that we know. In correspondences, actually every X is self-dual with these evaluation and co-evaluation maps. And you can show as an exercise that the trace of a forward-going map is just the fixed points of that map going from the point to point. So if we apply our sheaves, it means that the trace of F lower shriek, lower shriek is given by P upper star, P lower shriek. 2 sheaves on the fixed points of F. And finally, just for general context, the Euler character of a K-linear category, C in cut K, is actually something that already appeared in literature. This is known as the Hochschild cohomologies. So let's finish up by talking about the Lefschetz fixed points theorem. So here is Lefschetz's original theorem. If X is compact locally contractible, and we have an endomorphism of space of X, then if this trace of F upper star here is non-zero, then F has a fixed point. Now, this is has a more specific equality version called the Lefschetz-Hopf theorem that says that if we have a finite number of fixed points, then the trace of F upper star, what we have here, is equivalent to a sum of the indexes on those fixed points, which are a kind of local invariant that only depends on the behavior of F around the fixed point. Now, this has a further generalization. If X is a compact manifold and E is a dualizable sheaf, and B is a morphism from F upper star E to E, then you can construct a version of the trace of F for this input, which is written down here. The important part is that this is induced by taking global sections on B. And this is called the Lefschetz number for such input. It generalizes this side. And this is actually equivalent to a trace of a functor from, of a map from the global sections on a sheaf on just the fixed points. So if the fixed points are finite, this will just be a direct sum of skyscraper sheaves, which generalizes our sum of indexes. And let me just indicate how one might imagine using the six-functor formalism to get such a result. And the idea is to use the functoriality of traces in infinity 2 categories, which is something that I learned from this paper below, categorical proof of holomorphic Atiyah-Bott formula. So if E is a symmetric monodal infinity 2 category, then we also have the notion of adjoint pairs, just using the unit and co-unit definition of adjoints. And for example, in K-linear category, a functor F is such a left adjoint if and only if it preserves compact objects. So the functoriality of traces tells us the following. Suppose that you have two maps from two endomorphisms of dualizable objects. These are things that you can take the trace of. And you have a left adjoint phi from X to Y and the natural transformation like that. Then there is a way to construct a natural transformation from trace of F to the trace of G. I don't think I have the time to give you the definition here. But the important property for us is its functoriality. If you vertically paste two such natural transformations, then the trace of the left-hand side, oh, sorry, this was F. The trace of the left-hand side is equivalent to the composition of the trace of the top and the trace of the bottom. And in order to relate that to Atiyah-Bott and Lefschetz, one uses this diagram here below, where the upper, this left adjoint picks a compact object in sheaves X, so E needs to be a dualizable sheaf. This T is a clever way to encode our map from F star E to E. And the decomposition will give us a relation between the Lefschetz number, which is what you get when you analyze the trace of the pasted diagram, and the sum of indexes, which is what you get if you analyze what happens when you paste the lower and bottom part. And just notice that here in the middle, we have our F lower shriek, and we already noted that this corresponds to a functor through sheaves on the fixed points. Okay, so a quick summary. We introduced 6 functors. We listed a short list of 7 facts about them that have a lot of formal consequences, and we showed how one could use symmetric model infinity 2 functors to pack all of these together. Okay, questions?
So just that, and just to reiterate, so in fact, the Lefschetz trace formula is just a formal consequence of the fact that traces compose.
It's not completely formal. You still have to verify some things. For example, in order to define this trace here, given the map from this to this, you have to verify that global sections is a left adjoint in k-linear categories, which means that it preserves compact objects. So that's something that will not come automatically from the six-functor formalism, but it does tell you exactly what you have to verify. And all of these, what I'm trying to say is that this is a general argument that one could do if you know that there exists, that you can pack the six-functor formalism as a symmetric monoidal infinity two-functor, and it reduces you to check what are exactly the conditions that you need to perform each part of this argument. And this will give you the assumptions in your fixed point theorem.
But anytime I have like a two-functor or something like that into these k-linear categories, then I get a Lefschetz fixed point formula. Then I can unpack it afterwards to see what it actually means, but I get a composition of traces.
You have a general way of trying to produce a fixed a fixed point theorem, such as a Atiyah-Bocht fixed point theorem, or its more specific version, the Lefschetz fixed point theorem, just by trying to analyze this argument and see exactly what are all of the conditions that you need to run this argument and do this analysis.
Asaf, I actually, well, I'm worried, I'm confused about something like more technical, and maybe it's okay because you presented this only like as a vision, but it seems to me that for this thing with the formal trace to work, I mean, classically you do need the map F to have some property of transversality to the diagonal. So, I mean, unless you mean that you actually don't really work with the two category of correspondences, but rather, you do some kind of an infinity categorical version which has some spaces of isotopies or like, Ayala Francis style. I mean, I think it cannot literally work like as the way you said it.
This works, but it just imposes more assumptions. You need to assume transversality of the graph of F in the diagonal, whose intersection are exactly the fixed points, in order to perform a careful analysis here and say that you get and relate this abstract definition to the indexes themselves, as far as I understand.
But even before using this paper with this machinery, just like the thing you said, suppose you have a functor from the category of spans with like these restrictions into k-linear categories, then the trace in the source is really the fixed points. Like there's no, even if F is not transversal to the diagonal, just really is the fixed points because it's a one categorical construction. We're taking the pullback, it is the fixed points, and it cannot go to the trace of the push forward shift unless there is some transversality assumptions on F. So maybe it's beyond the scope. I'm just saying that it seems to me that in your vision for infinity categorical repackaging of the six-functor formalism, you probably need to tweak the source category to be also an actual infinity two category in a way which handles transversality issues.
But maybe it's not. Maybe it's not. Maybe fix F has some importance or something that at least in the algebraic situation, then you can encode this data in the. Maybe it's not just a space, but a space with some weights.
Yeah. So theoretically, what you would like
Leo,
is to take.
I think this discussion becomes a little bit too tangential to the scope of the workshop. So
You agree.
I
I agree.
it's
You're right.
time to thank Asaf.
By the way, for the Weil conjectures, the derivative of Frobenius is 0, so it doesn't have it is transversal to the identity, which has derivative 1.
It amplifies Shai's point that this discussion is transversal to the aim of the workshop. So
Okay, so I'm going to finish the recording.